This meeting is now being recorded.
We have two great speakers with us today, Ann Kania and Mark Rainzo, who have done great work to promote the value of stormwater as a resource. And the Storm Seminar Series is an open forum to feature new research, technologies, policies, and news relating to stormwater. The opinions expressed in this presentation and on the following slides are solely those of the presenter and not necessarily those of the State Water Resources Control Board. The State Water Board does not guarantee the accuracy or reliability of the information provided hereon. With that, I would like to introduce Ann to begin the presentation. Thank you.
Thank you, Stephanie, and thank you everyone for coming, and thank you for inviting us. It's a pleasure to be here. Hey, Mark, how are you today?
I'm very good. How are you, Ann?
Good, thanks. Just so you know, Mark and I are a long way away from each other. He's over in western Montana, and I'm further over to the east in my home office overlooking the Yellowstone River, with the phones and the dogs on Do Not Disturb and ready to go. So the format of our presentation today will be, I will lead you through a deck of PowerPoint slides, and Mark will lead the question and answer session afterwards. We'll start off with an introduction to floating treatment wetlands. So please bear with me if you've already heard, if you're already familiar with floating islands. Then we'll move into discussing design and deployment considerations. And then we'll present some case studies from stormwater projects showing a range that we've had researched by third-party independent bodies. And we'll cover the ever-important topic of sizing. And just in case you're going to be distracted by wondering where my accent is from, let me tell you right away, I'm from the northeast of England and from Sunderland in particular. Sorry, I don't know how to turn off the dinging without losing, wait a minute, I'll just mute. I think I can mute my computer, then you won't get distracted by that. Just remember to turn it back on again later. So, floating islands are modelled on the floating bogs of northern Wisconsin. And we first learned of them as a fishing magnet. But over the last 20 years of studying them, we've learned that they do other things as well. They harness the combined effectiveness of plants and biofilm to treat water. And often the most obvious sign of this is a reduction in algae blooms. They reduce sludge and sequester inorganics, and as a result, they improve water clarity so that sunlight can penetrate and DO can increase and throughout the column, and that nurtures an ever-expanding biocomplexity. They can also be used anywhere in the watershed. So we see them as being very valuable as protecting the receiving water from contamination and eventually preventing dead zones. The photograph that you're looking at now is an array of biohaven floating islands in a shallow leachate pond actually on the west coast of New Zealand. And you can see the lush plant growth on top, and you can see the roots underneath that are covered in green biofilm. Technically, I guess it's called periphyton, but I'm going to refer to biofilm really throughout the presentation. They treat the usual suspects. Nutrients, obviously, probably the most commonly treated contaminants that we use biohavens for, but also total suspended solids in particulate heavy metals as well as dissolved heavy metals. And the ones that we've had the most testing on are copper and zinc, with lead to some extent. And I just want to add as well, fecal coliform and E. coli, which the islands have been very successful in treating. In fact, hot off the press, there's a new case study from Magic Johnson Lake in Los Angeles, where fecal coliforms have been taken down to virtually non-detect. I'll show you some pictures of that later in the presentation. They can be deployed, as I said, anywhere in the watershed, from the smallest stormwater detention pond, from ditches and streams, wastewater lagoons, I'll mention briefly just to get you thinking that way, ponds and lakes, and estuaries, reservoirs. They also do a good job in preventing erosion because they absorb wave energy. Habitat restoration they use a lot for, and on the Gulf Coast for restoring the marsh. But we're focusing on stormwater today. And in fact, this is an excellent case in point. This island here in Lake Rotorua in the North Island of New Zealand, which I'm sure some of you have visited, this is the largest of our biohaven floating islands that's ever been deployed. It's 5,100 square meters, and its purpose is to intercept the nutrients that come in from ag that drains from all sides into this lake. And the lake is a very precious lake to the Maori people, not to mention to the tourism industry of New Zealand. So Biohaven Floating Islands, which is our brand name actually from Floating Islands International and Floating Islands West, they have been accepted as a constructed wetland for many years now. A taxonomy paper was published by the Helmholtz Institute in Leipzig, where floating treatment wetlands, there were 3 types of floating treatment wetlands discussed under the constructed wetland banner. They are modular, so they can be joined together in any shape or size, and they're made of synthetic fibers that come from PET drinking bottles, recycled drinking bottles mainly, and they're injected with Coast Guard approved marine foam to give them buoyancy. And we can make them different levels of buoyancy, but for stormwater, pretty much we treat them like a wetland and make them buoyant enough to support the wetland plant system, not necessarily to support people, though that can be done. They've been thoroughly tested for toxicity, and of course they pass with flying colours. Not only environmentally friendly, but also shipping friendly. And they can be passive or active. This one here in the picture is one of the first ones, I think, installed in California, which has been going strong, as you can see, since 2008, and that's a recent photo. That's the passive version. This is the active version, which we call the Biohaven Floating Streambed. This one is here in our research center in Montana. It uses an air blower, you can see the pipe going down into the water, to displace water, and it's very cheap to run. And the reason it's called the floating streambed is that actually floating island, it's not actually a gap in the island. There's actually island underneath the bubbles. So what we're doing is sending the water in a stream across the top of the island where it gets a chance to pick up air from the atmosphere and then fall back into the water column. And here's an example of an island that's manufactured by Floating Islands West in McCullumney Hill. This is what they look like when they leave the factory. Now you can see, I think, just that what we call the matrix, the material that the islands are made from, is like a very fine pot scrub material with a lot of fibers for growing biofilms on, but they're also porous, so water will flow through unimpeded. And there's the numbers there. I'm sure you can all read the surface area. The 2 primary functions of the matrix are to kickstart the system with biofilm when you first launch them, because at that point the plants are immature and they're not going to contribute to anything. But over time, as the plants mature, the Biohaven platform is what we call a super enhanced platform for plants. In other words, plants can grow really, really well with an emphasis on producing bushy roots that hang below the island into the water column and then trap all the suspended solids and what have you in the water as it circulates past. Describing a couple of the features of the islands that you can see there, you'll see that there are holes drilled in to the top of the island. These have two functions. One of them is, we put the plants in there, but we plant them into a potting mix that's made of peat, usually cocoa peat, which not only nurtures the plants, but it also wicks water up to the plant roots. So even if the plants have got very shallow roots, they're still going to get wet because of the capillary action of the peat. And then you'll notice there's a few cables sticking out the ends there, sticking out the sides, and they, of course, are for attaching anchors or tethers to. I think that's all I'm saying on that slide. So, but now we come to the heart of the matter. How do they work? And I'm going to take a little bit of time to go through this slide in detail. So you can see that they work through surface area and circulation. The plant roots, as well as the biofilms on the matrix itself, provide a massive surface area. But not only that, there are synergies between the plants, the microbes, enzymes, sugars that are secreted by the plants that provide, the sum is more than the parts. There's a lot more complexity when you have the system working together synergistically than, say, when you have an artificial surface area, which has been tested. NIWA, when they were doing their initial tests in New Zealand, they actually constructed some polyester roots, and they had nowhere near the performance capability that the plants and the biocomplexity have. So the floating treatment wetlands, well, first of all, on the left-hand side of the slide, you can see, obviously, circulation has got to happen through the plant root biomass for the system to do any good. But the floating wetlands actually slow down the water flow themselves so that they actually promote the settlement of suspended solids. And then, of course, the plant roots will perform a mechanical filtration. And then the microbial communities in the biofilms, they contribute largely, the largest contribution actually, to the water treatment process through biofilm attachment, filtration. They actually aid the nutrient uptake, i.e. the direct uptake by the plants. And of course, sequestration will happen into the sediments. Calculations were, because this has changed, that the plant uptake is actually less than 20%, more like 15% of the total treatment. And in fact, when we've taken plants over to Energy Lab and got them to analyze what's actually in them, there's been actually a lot less than 15% of the nutrients that we've tested. However, we are working with a company in San Jose called Intrinsic, who have a patented range of newly developed hyperaccumulators and endophytes, which are particularly effective at removing heavy metals, sulfates, and what have you. And we're working with them to trial them on floating islands. We see a tremendous synergy there. The root hairs. You can easily see the root mass under the island, but what you can't see are the root hairs, which contribute up to 69% of the root biomass. So the system is bigger than you think, that's for sure. And on the right-hand side here, you can see the root mass that's grown on that island that's being used for a research project in France. So when you look at biofilm through a microscope, and this is actually a video, and I love this. I wish I could show you the actual video. These things that look like wine glasses, I think they're called rotifers, but I'm not an expert on this, but you can see them flapping their tails and eating the greenery above. And everything is either eating or being eaten. We think of it as a jungle, lions and tigers everywhere, and everything from the bottom of the food chain, part of the food chain. And so it's easy to see then that biofilm is constantly being renewed. So we often get the question, well, do islands plug up? And the answer is no, because this is a living system. It's always being refreshed in some way or another. And the surface area is the key to producing biofilm. So when you have suspended microbes in the water column, they're vulnerable to changes in what's going on. Whereas if they have surface area and they can attach to a surface area, not only are they more resilient, their DNA changes and they become more able to adapt to the environment and take on the nutrients as food or, whatever, just actually decontaminate the water. And of course it's sticky, so anything that comes in particulate form sticks to the roots and then eventually falls into the sediments and is sequestered in the sediment. So the microbes within the biofilm themselves, they will digest the organics. So you'll find that sludge will reduce underneath the floating island. So the whole system, the matrix and the roots, we think of as a bioreactor, which of course is well-known technology for pollution reduction. So before we move on to the next slide, I'd just like to check in with Mark. Mark, is there anything that I missed out or that you'd like to emphasize?
No, I think you covered everything, Anne.
Just realized I was on mute. Okay, I'm going to move on to the next slide. I feel in a bit of a tunnel here. I hope there's nothing happening that I'm not aware of here. Okay, and now we're going to move into actually looking at some installations of floating islands. One of the main benefits is the adaptability to changes in water levels. They can deal with a slight trickle to peak flow. And in fact, they can even dry out for periods of time, as you'll see, and still be effective when they rehydrate. They're very easy to transport. They're easy to pick up and move, i.e. launch by hand, manually. They can be made in different shapes and sizes, so you can put them in any kind of water body, as we've already mentioned. And I think very importantly, they can be configured so that if you need an aerobic treatment or anoxic treatment, there are ways of creating either or. The people ask, well, how long do they last? Well, actually, we don't know yet, really, because we think they're going to last indefinitely. The longest, the oldest island we have here at our research centre is 13 years old, and there are now a lot of installations out there, including this one here in New Zealand, that are in their 10th year. So I think the longevity is certainly proven to 10 years, and they're not showing any signs of degradation. So as far as the design considerations are concerned, I mentioned that we can be flexible about whatever the goals are. So if in a case like this, you've got probably fish and you need to keep a high dissolved oxygen environment, then we recommend that we use lots of small islands. Whereas if you want to treat mainly heavy metals, or there's nitrate in the water and you need to denitrify, then we would recommend using a larger island to promote anoxic processes. Plant selection is critical. So again, we've got so much experience that we think we've got a handle on this. We choose perennials that are pollution tolerant, which typically would be wetland plants, that provide bushy rooting systems that probe up to 1 meter down into the water column. If we're using an aerobic system, we will plant sedges and rushes. Anoxic would be more like grasses because they handle the low DO conditions very well. And then as a side issue, if you happen to be dealing with waterfowl, We've learned through trial and error what works and what doesn't work. And what works is that all our islands now are given a UV protective coating, which also protects from any kind of pecking. In addition, we can plant plants that waterfowl just don't care for, and we can also put fencing up. So we've got waterfowl nails, I would like to say. Another consideration, of course, is aesthetics. We can shape them so that they look naturalized. One thing we can't really do anything about, and I don't really like to bring this up, but they can be susceptible to collecting trash. Obviously, they're going to be oil and grease, but any sort of plastics and things will need to be removed if aesthetics are an important consideration. And finally, sizing, which I mentioned, seems to us to be one of the most important questions. Historically, we have used all the case studies and scientific studies that we can get our hands on as input to our sizing tool. So we have a proprietary sizing tool that from which we extrapolate from existing studies to the new project. But more recently, there's a study that's just come out of Australia, which I find quite exciting, that actually sizes on of the ratio of the floating treatment wetland footprint to the catchment area, the immediate catchment area of the stormwater basin. And we'll talk a bit more about that later when we come to the case studies. So when it comes to deployment and launching and maintenance and all those issues, anchoring and tethering is obviously important because you don't want to lose the positioning, which you don't want it to cover the outflow, and you don't want it to move away from the maximum circulation. We would recommend, where possible, tethering rather than anchoring, actually, because it's simpler and more straightforward. And there's quite often you can use just rebar or put in a piling or bollards, or even use an existing structure. And anchoring does depend on much more on the wind and the fetch, and actually what's on the bottom of the pond, which could be a little bit sludgy when you first launch an island. Sediment can be, we need to watch sediment. Like I said before, that the sludge would actually get digested by the island, so there should be less actual sludge. But because we're settling out heavy metals, then the sediments need to be checked from time to time. I've kind of read once every 10 years, but still you have to think about it because there could be an accumulation below the island. So maintenance. Actually, maintenance, O&M is straightforward, and with the caveat that the first month is key. You need to pamper the plants when they're first launched, just to make sure that they establish. Then after that, you can pretty much get by with very few maintenance checks. If you do happen to see any invasive plants, they will need to be removed, of course. And from time to time, maybe once a year, you might want to check the anchors or the tethers just to make sure everything's still in place. Get somebody to look in on the pump just to make sure that the pump's working if you're using an aerated system. But really, that's all there is to it. Ice is not a problem. We have, of course, we have a lot of icing up for 4 months of the year here, and the islands just freeze into the water. The water just gets through into the pores, thaws again in the spring. Everything starts to sit right once the water warms up, and the plants will grow again. Now, placement. The placement is important, of course, because you want to maximize the circulation, especially if you're not using aeration or an added circulation system. So we would recommend that you place them just in from the inflow or just up from the outflow, and stretch them across the pond. So if they're like in a chain, you might need 2 layers of chain to offset each other. If it's one big island, you can put it across, and you can put it across the pond just, by the inflow or the outflow. That is going to work really well. And in fact, speaking of which, I'm now going to show you a fun video of an installation in Queensland in Australia. By the way, SPEL Environmental is a division of Water Clean Technologies, who are our licensees in Australia and New Zealand. Let's find how I can get onto the next. Oh, no. So now we're going to delve into the case studies in a little bit of detail, not too much. Hopefully they will speak for themselves. First I want to discuss is Metro Park in Billings, here in Billings at the convention centre, which treats basically industrial area runoff and some agricultural drainage. I'll give you a second to read the slide. Doesn't rain very often, actually, although in the summer we can get quite a lot of thunderstorms. But the number of rain events, there can be a long time between rain events. So the City of Billings actually ran the study over the course of the year once the plants had matured. So they got, I think, excellent results considering that the stormwater is seasonal and the islands have to rehydrate before they can, start to continue the treatment, which they did successfully. And I mentioned copper and zinc earlier, and this is I think it's the only study I know of that's directly looked at lead reduction. Oil and grease was a factor as well, of course. The next one is Mermaid Pool in New Jersey, which was a study that was managed by Princeton Hydro. And they particularly wanted to look at the amount of phosphorus that a floating island could remove. or deal with. You can see the algae was a big concern. This was taken a couple of months after the islands were launched. And there were two things that were really important. One was that they removed 66 pounds of phosphorus in one season. The other one that we were probably more concerned about really in the long term is knowing what kind of concentrations, what kind of inflow concentrations are best for a floating treatment wetland. And we discovered that below 0.1 milligram per litre, they were not as effective as when the concentrations were above 0.1 milligram per litre. But that's quite a decent, quite a decent attempt at fairly low concentrations anyway. And then just doing the math on this, we know what a pound of phosphorus will remove in terms of algae. Well, 66 pounds, you can see why the islands were effective at diminishing the algae blooms when you consider that accounted for 145,000 plus pounds by wet weight of algae. And I can tell you, as somebody who spent a whole summer a few years ago removing algae and aquatic weeds by hand, I prefer to do it this way. Thank you very much. Silverdale was a more complex scientific study undertaken by Chris Tanner and colleagues at Auckland University and NIWA in Hamilton. Chris has been a champion of floating islands since he first heard about us and came to visit to find out about them. So this is one of many studies that he has done, he and his team have done. And their concern, because it was highway runoff and because it's New Zealand, there's a lot of zinc and copper in the water, their concern was heavy metals in particular. So they went for an anoxic treatment system. And in a 100-meter pond, they covered it with 50%, with 50-meter square island. And their paper is very detailed and discusses all the reasons why they believed the islands performed so well and why they chose anoxic conditions. So, of course, as for any island, the dense root network and the biofilms are responsible for settling and digesting the particles, but they also figured that the low dissolved oxygen was instrumental in increasing the metal and the phosphorus sequestration, and also it helped with denitrification. Of course, again, they had to aerate the water before it went back into the receiving water. That is no big issue. The University of the Sunshine Coast study across the pond in Queensland was published last year. And this is the one I mentioned earlier, where they actually tried to not only look at the overall pollution removal, which, as you can see, was pretty effective, in a situation where the inflow, I might add, was highly variable because, the Sunshine Coast, you wouldn't expect it to rain very much, and there's a long time between showers. They did two things. They tried to eliminate short-circuiting, and then they made an attempt to calculate how to size an island by area. To show you the system setup, you can see that the inflow comes in, and it's contained by these impermeable battles known as curtains, and so they attempted to get 100% of the water to flow through the treatment wetland and out at the outflow. What they then recommended was that, with all the calculations that they did, which you can read about in a peer-reviewed article if you're interested, which I can send you, they recommended that the floating treatment wetlands should be 0.37% of the catchment area size. That is the immediate catchment area size, which would be required to meet Australian standards. So obviously that begs the question of what standards are you going to meet. But what they actually had was 0.14%. And it was, just over 1,000 square feet was the island. And they got decent removal figures with that. So we think, cautiously, that this is a good figure to start off without going as far as the 0.37%, because when we correlate it to our own sizing and our own case studies, it's starting to come out consistently between the two. The only caveat is that with this system, if we have to capture as much of the flow as we can, because it was based on, the 100% flow and limiting short circuiting. So we do need a bit of information if we are designing a stormwater project, but as you can see, it's actually quite minimal. We need to know, obviously, parameters concerning the pond, how big it is, what's the drainage area. We need to know, of course, what the goals are. And it's always very helpful to have a Google Earth map, just in case there's anything weird about the pond shape or size. But generally, as long as we can see where the inflow and where the outflow is, we're pretty home and hosed. And then in addition to that, if you've got actual water quality data that we can use, and other things like the flow rate, and we need to, if possible, how deep the water is, and if there's a whole bunch of sediment in there, that's helpful to know as well. But we don't really need that much information. Nothing that that you wouldn't already have at your fingertips anyway. Just want to mention in passing the photograph, you can see that that's actually an island that's already got rid of the duckweed, and it's now working on the next level of vegetation. And you can see how well the plants are thriving, in spite of the fact that the water looks pretty nasty. Moving slightly sideways on this one here, we are experimenting with a system that we call the elevated bioswale, which is a way of using the floating island material in a ditch, primarily an agricultural ditch, but any kind of swale that receives stormwater. This is one that's grown in. You can see how naturalized it is. This slide is actually, this slide is more, you can see how it's made and how it works. It was a short study for 6 weeks, but the turbidity removal was not bad, and we're extending the study this year. But just to talk you through the photographs from top to bottom, it's kind of, but this is the swale upside down. It's been form-fit to fit into that ditch. And then, of course, once it's planted with, in this case, Kentucky bluegrass, whatever it is that it's planted with, it naturalizes. And you can imagine the water coming in from look at the second photograph, the water's coming in from the top, it's passing through the bioswale, and it's much clearer at the end than it was at the beginning. I think the thing that might really appeal to dry areas like California, where there's a big emphasis on recharging the groundwater, is when there are floods, these things back up, and they allow first of all, they allow the water to seep through the ground and recharge the groundwater, but they also obviously prevent the scouring of the streams and ditches, and also all that sediment getting into the sensitive receiving waters. So we're really excited about the possibilities for the bioswale, and we've now developed a system that we call the silt wilt, which is a disposable or a removable absorbent mat that can, go in the front end of the bioswale and then be removed once it gets filled up and either, shaken out or washed out and reused if that's what you want to do. So I want to let you know that there are a lot of biohaven installations already in California that have been deployed by Floating Islands West, namely Laddie Flock and Gary Lewis and the team of distributors and champions out in California. Magic Johnson Lake, this is a very recent case study that we've received from Aquabio. From looking at the before and after photographs, it's amazing, and the reduction in fecal coliforms is excellent. But all of these projects have contributed to protecting the water resource of California in one way or another. And yes, I would just like to thank Laddie and his team for their fantastic work as our exclusive licensed manufacturer of Biofilm in California. I'd be a bit remiss if I didn't mention wastewater just a little bit. The same reasons that biohavens are ideal for stormwater, of course, apply to wastewater as well, with possibly the additional advantage that there's no disruption of operations when you launch a biohaven into a wastewater lagoon. And with the accelerated nutrient removal, they can extend the life of a small community's lagoon to delay the next upgrade, to either save the community money, to extend the capacity of the town so that it can grow. And it's a very well proven technology. We have, I think, 24 installations throughout New Zealand, the US, New Zealand and the US, and I think there's one in Australia. But we've got a good track record, and we are excited about the possibilities for small communities. So that is my presentation. Thank you for listening, and I'd like to invite you to ask us any questions, and especially questions you might have for Mark.
Thank you, Anne. Now, Jeffrey will be covering questions that were sent in. If you haven't emailed in your questions, please do so now at storms@waterboards.california.gov. And I've also seen that some people have been using the public chat. You could also post your questions there, and Anne and Mark will answer them.
And Stephanie, this is Jeffrey. I just wanted to confirm that I have not received any questions yet.
Okay.
So I'm waiting.
So I guess people have been using the public chat, so I guess we can continue doing that instead.
Anne, this is Mark. I've been answering some questions on the public chat while you were doing the presentation. You might scroll back through that and see if you agree with my answers or have anything else to add.
Oh, Mark, to be honest, thank you for that, but I've just been sharing my screen, so I'm just not going to even try and mess with the public chat right now. I trust you implicitly.
Okay.
Were there any interesting questions?
Well, let's see. We had a question about microplastics possibly absorbing toxins, and then the question was, should floating islands be considered in the same vein as microplastics when assessing the fate of small fibers which break off?
Oh, yes, that's a huge question.
I said I don't believe so for two reasons. One, all the information we have is that floating island matrix is completely inert, and typically our islands aren't used in the presence of anything that could really be considered toxic. We're mostly concerned with things like nutrients.
Yeah, and if I could just add to that, once they go in the water, of course, they get covered with biofilm, and in any case, they're made from the plastic that we drink from in drink bottles. So I think you've answered that very well. The most recent development, I talked about having a protective coating to stop waterfowl damaging the island. That coating is what concrete water tanks are lined with. So that's another coating that's treated to the highest standard and that is suitable for use around drinking water.
There was also a question about a minimum depth for a pond. I said about 18 inches. What would you say, Anne?
I would say, it's an interesting question because when you're talking stormwater, I mean, those islands in the metro dried out completely. And then as the rains came and filled up the pond again, that never got as deep as 18 inches, and yet we got excellent removal. So I think it depends on your placement in the pond, and as long as there's not a lot of short circuiting, as long as everything goes through the floating island, then I think you can go shallower. I know Chris Tanner, when they did their research, they talked about the roots occupying 0.67% of the water column. But frankly, I think that was for anoxic conditions, and I'm not quite sure why. But I think in our experience, we've gone shallower, and the roots just don't want to grow into the sediments, so they don't tend to bind.
Mm-hmm. Here's a related question, Anne. How long can the pond stay dry?
Yeah, I think I don't know the answer to that question. I know it was studied in the Bribie Island study. They looked at the events and how dry the island got before the next rain. But I'd have to go back to that study to answer that question. I think it was one of those situations where they said it would take 23 years, given the number of rainfall events that we have, to be able to answer all these questions, and really it's not worth it. So that was their answer.
Okay. Here's another question back on the toxicity issue, saying that even inert microplastics are harmful to aquatic microorganisms. Have any benthic studies been done in the areas of floating islands to determine if there are elevated levels in the benthic fauna? I'm not aware of any benthic studies we've done to look at toxins.
No, I don't know that we have either. Though we are talking with Energy Lab in Billings, and to do some more extensive testing on the plastic. All our tests that we've done with fish, with microbes, we have thriving populations. We have thriving populations of fish. They are, I just can't see that there's anything that's harmful in the environment. But of course, one has to be aware of hubris and the law of unintended consequences. But when we look at sponges growing on the underneath of islands, we look at the multitude of fish. That study that was done with bisphenol A, when they added that to a tank to make sure that to cause the fish to be kind of innervated, and then within 3 days the fish recovered. It's not the kind of detailed analysis that the question was probing into, but I think it's very indicative. And then I also think that, even if there is, we've got to do something to clean up the awful pollution that we know is in the water that's a lot more harmful. We've got no evidence on the one hand that floating islands are causing any harm, but on the other hand, we've got huge evidence that what we're putting into water is causing enormous impact. So, I think that the broader view would argue for doing what we can and making sure that we know it's safe to the best of our ability.
Here's a question. Have more natural materials been tested as a medium, something more natural than the matrix we're using for the islands? Yes.
Did you answer that one? We have used coconut
Oh, I didn't.
coir.
That just came through.
Oh, right. Good. Yeah, we've done tests on coconut coir, however you like to pronounce it, and they use it regularly in China. Our Biohaven licensee uses it in China. Now, it does break down over time, but in all honesty, it holds up very well for a time. And it's really one of the next product development tests that we are planning to do. Of course, longevity studies are not cheap if you have to sort of force the degradation. But I think it's important that we do that. So yes, we have used coconut fiber. It does work. We don't know how long it'll last. and we're going to study it some more.
There's 2 more questions under Q&A. One of them is, what is the estimated cost per area of an island?
I will need to defer that question to Laddie Flock, whose contact details are on the screen. Laddie is totally responsible for the sales and of floating islands in California. So please, can I ask you to refer that question to Laddie through Floating Islands West?
Okay, there's one more question. How is the peat applied to the supportive matrix?
You mean when we're planting the plants and we're putting the peat in the little pockets?
I would assume so.
Yeah, I think so. We just pack it in really, really tight so there's no air holes, and there's enough structure in the island for it not to fall out. So if you use something that was clay-based or sand-based, then that would tend to leave to disperse inside the matrix. But actually, the cocoa peat is fibrous enough that it just expands and stays in the holes. I hope that answers the question.
So there's a new question. Any comments on the primary removal mechanisms responsible for contaminant reduction? Does removal depend on the fiber media or the plant microbes? So it's a two-part question.
Okay, that's a good question. We have looked at the removal mechanisms for phosphorus in particular, and we know that the mechanisms involved there are the biofilm that grows on the island, on the matrix, and also the biofilm growing on the plant roots, biomass that grows and then detaches and sinks to the bottom of the pond or waterway, uptake into the food web. This is something that Bruce Kania, the president of Floating Island International, is really promoting, calling it the concept of transition water, and that's trying to take eutrophic or hypereutrophic waterways to a better condition. And studies that they've done at the Floating Island Research Center have indicated that using fish harvest is a good way to get nutrients, including phosphorus, out of the water by basically uptaking them into biofilm and plants and then into larger aquatic organisms and ultimately into fish. So that's another mechanism for nutrient removal. Then there's also plant uptake, and if plants are being relied on as the mechanism for nutrient removal, they would need to be periodically harvested, and that has been done in some applications. But as Ann noted earlier, we've discovered that only generally 15 to 20% of the contaminant removal is done by plants, unless you were to go to the hyperaccumulator plants that she mentioned. So those are the basic mechanisms involved. And there's a question here, and are the plants provided with purchase? Are there different plants for different water sources?
We can always work with the customers to recommend plants depending on where they are, where the situation the islands are going into. And I made a general comment about using rushes and sedges and grasses for a system with a lot of pollution. But plants are really interesting. So you can take whatever's growing around the pond or lake that you're working with, if there are any, and use them, and you can bare root them and put them into an island, and usually they'll thrive. We've gone from everything from carex, islands that are completely planted with carex or different species, just so that it's not a monoculture, through to growing a vegetable garden on our walkway here, which was fantastic. In the heat of the summer, we didn't have to water our tomatoes once. We grew pumpkins that had roots like beach balls. So, you know, that as long as there's enough dissolved oxygen in the water to support the plants that you're planting, then there's a huge variety that you can consider.
Then there's another question, do you have to replant or trim plants at certain intervals? And I can start answering that. You'd only have to trim or cut back plants if you're relying on them for the nutrient removal, which we are in some cases, or relying on it for a portion of it. As far as replanting, as long as perennials are used, generally do not have to replant. There was one interesting case study in Wyoming last year where waterfowl really concentrated on an island. It was the only open water during the winter, really hammered the vegetation, and thought we were going to have to replant, but the plants actually came back. And that's one reason for using that bird netting that was shown in the video to avoid damage to plants.
Yeah, I think you're spot on there, Mark. The root biomass is what you want to promote, and it just keeps growing. The only situation where you might want to trim the plants deliberately is in a wastewater setting. If you have plant die-off in the winter, if you're in a colder climate zone, you wouldn't want plants to die and then fall back into the water that you're trying to treat. I don't think that would apply quite so much for stormwater, but it is a consideration for wastewater. But you always have to balance the effectiveness of the plant and the root mass versus the danger of it getting into the water column. And we'd recommend, trimming down to about a foot if absolutely necessary. And speaking of that, when we build a wastewater installation, we make a walkway. We tend to use wider island arrays, and then we build a walkway down the middle so that you get very easy access.
If anyone still has any questions, please post them on the public chat. We'll wait maybe a minute to see if anyone has questions, and if not, I guess we'll wrap this up. So a new question was posted. Do floating islands seem like a viable option for a 3-acre pond system of approximately 30-foot depth that has high COD and receives loadings of iron of approximately 2,500 pounds per year?
Okay, good question. Boy, that's a lot of iron. We've calculated removal rates for different parameters in terms of pounds per year per cubic foot of island, and for metals, they're relatively low. They're higher for things like BOD and total nitrogen. So we could turn down potential business, but iron is not a contaminant that we have much data on or would expect a real high removal. And if we did, I know you'd need a lot of islands to remove 2,500 pounds per year.
Yeah. I mean, do you think there might be a way of doing it if you could sort of build a sort of a settling pond to the side and then manage the flow sort of with a largish island and create anoxic conditions so that the iron can settle out? I'm sure there'd be ways of doing it, but just to put islands in that size pond with that depth, without circulation and aeration, which would be counterproductive, then I think Mark's right.
Yeah, if the iron were particulate, that's a possibility. If this is dissolved iron, that's what I was thinking of. I probably wouldn't recommend islands.
Right.
I think there's a question, not a question, a comment. So Randy posted, let's all remember the value of increasing the surface area volume ratio when considering treatment between porous material and incredible root mass. This does the trick.
Yeah, here. That's a very positive note to end on.
All right, so if no one has any further questions, Anne, Mark, do you have anything additional to add before we wrap up?
No, just
I
to
do
say
not.
thank you. Yeah, thank you very much for hosting us, and thank you for your attention. And it's been a pleasure to talk with you.
All right, thank you, Anne and Mark, so much for presenting, and thank you, audience, for joining us. I guess this wraps up our seminar.